Welcome. In this session, we'll learn one of the most important topics of the syllabus, that's the resolution of an arbitrary sequence. So our goal is to represent x of n, that's our sequence, in terms of other sequences. And the goal in this class is to learn how do we express in terms of delta functions or delta sequences, or that's also referred as unit sample sequence or unit sample sequences. So the goal here is to express x of n in terms of delta n functions. How do we do that? Now to illustrate this, I'm going to take a very simple example. Please pay attention. This is very, very important. How do you express x of n in terms of delta function? So this is very, very important, this topic. So let's take a very simple example. Let's suppose our x of n is this sequence. So it is 2, 1, minus 3 by 2. So suppose this is our sequence. Let me take this very simple example. So graphically, you can say your sequence looks like this. So if this is our x of n, and this is n equal to 0 point, this is 1, this is 2. Similarly, this is minus 1, this is minus 2. Now you can see at the value at n equal to 0 is 1. Let's suppose this is the value. So at n equal to 0, the value of the sequence is 1. The value at n equal to minus 1 is 2. So this is the value at n equal to 2. Similarly, the value at n equal to 1 is minus 3 by 2, means 1.5, or simply minus 3 by 2. So this is our sequence. The rest of the samples are 0. Let's take this very simple example. Now what I'm going to do, in the first step, what I'm going to do, I'm going to multiply this sequence with this function. I'm going to take a sequence and I'm going to do this multiplication. Let me take the example like this. And let's suppose this is our delta function. So I'm going to multiply this by delta n. And by definition, if you remember, delta n is 1 at n equal to 0 point. At rest of the points, the value of the sequence is 0. So at n equal to 0, the value is 1, and at equal to 1, the value is 0, 2, the value is 0, at equal to 3, the value is 0, and so on. So these values are 0, and it's non-zero only at n equal to 0 point. So if you multiply these two sequences, what will be our result? Now let me write it like this. So what's our result? So our result will be this sequence. So we'll get this sequence as the output. Now let me try it here. So this will be our x of n delta. So this is our sequence. Now have a look at this. How do we do the multiplication? Multiplication simply means multiplying the corresponding sample time values. So when we multiply value of x of minus 2 with delta of minus 2, you can see the value here is 0, the value here is 0, so it will be 0. Let me first mark these n point 0, n equal to 1, n equal to 2, 3, similarly n equal to minus 1, minus 2, and minus 3. Now, when we multiply the corresponding sample values of x of n and delta n, that's the meaning of multiplication. So if you multiply delta n with x of n, what we'll get? We get, let's start with n equal to 0 point. So at n equal to 0 point, value of the sequence is 1, the value here is 1, and so when we multiply n equal to 0 points of these sequence, the value is 1 here, it's 1 here, so the value, signal value will be simply 1. So the value of this multiplication will be simply equal to 1. Similarly, let's first calculate the values of the signal for n positive values of n. So when at n equal to 1, the value of the sequence is 0. At n equal to 1, the value of the sequence is minus 3 by 2. So 0 multiplied by this sequence is 0. Similarly, the value of the sequence at n equal to 2 is 0. The value of the sequence at n equal to 2 is 0. So this is 0. And so on. So all these sequences. this sample points will be 0, or this multiplication. Similarly, the value of this sequence at n equal to -1 is 0. The value of this sequence at n equal to -1 is 2. So it will be again 0, and rest of the samples will be again 0 that you can check. So this is our x of n delta n. So what's this doing? So when you multiply x of n with delta n, what do you get? You get x of 0 point. Rest of the samples are 0. You can check it. You got x of 0 point multiplied with delta sequence. Multiplied with say delta sequence. That's the output of this multiplication. So when you multiply x of n with delta n, you got x of 0 multiplied by delta n. Right. So now let's multiply the given sequence now with another sequence that is shifted delta. So let's multiply this sequence with this sequence now. So this is our delta n minus 1, and we mark the points. So this is a 0 point, n equal to 1, equal to 2, 3, equal to 4, so on. So minus 1, minus 2, minus 3. So this is delta n minus 1, means give a shift of one shift to delta n. So this signal will be simply this. So this is our delta n minus 1. Delta n minus 1 means simply give a shift towards right to delta n. Now when you multiply this sequence with this sequence, what will be the result? So when we multiply this and this, the output will be something like this. So this will be our output. Output will look like this. So this is x of n delta n minus 1. All right. So this is our multiplication. So this will be n equal to 0 point, n equal to 1, n equal to 2, n equal to 3, and so on. So this is n minus 1 minus 2. So when we multiply, see these sample points are zeros here. Rest of the sample points are zeros, right? So when we multiply x of n with delta n minus 1, what will happen? Let's start with this n equal to 0 point. At n equal to 0, delta n minus 0 is my delta n minus 1 is 0, and x of n is 1. So the result will be simply 0. So this will be, so the multiplication of these two sample points will be 0. Similarly, the value of delta n minus 1 at n equal to 1 is 1, and the value of x of n at n equal to 1 is minus 3 by 2. So what will be this equals? This will be simply 1 multiplied by minus 3 by 2, and that will be minus 3 by 2. Now when we multiply delta n minus 1 at n equal to 2 with this x of n at equal to 2, both are 0, so this result will be 0. Similarly, the other sample points will be 0 when n is positive. Now let's calculate the value of x of n delta n minus 1 when n is negative. So when n is negative, this sequence is 0 for n equal to minus 1, this sequence is 0, and this sequence is 2. So the result will be 0, and the rest of the samples will be again 0, that you can check. So what's the result? So what do we got? We got, when we multiply x of n with delta n minus 1, what it did? Only one sample is non-zero. That is the same sample of x of n when n is equal to 1. So we got the sample point of x of n, that is when n is 1, when we multiply it with delta n minus 1. Right, so this is our result. So we got x of 1. You can see x of 1 is minus 3 by 2, and delta n minus 1 is 1 there, and rest of the samples are 0. Now, next what we are going to do, let me compress this further to visualize this so that you can see what I'm going to do. I'm going to take one more sequence and multiply x of n with delta n plus 1. Now, delta n plus 1 means give a shift towards left to delta n by one sample point, So this is our, this different marker. Let's mark the time points first. So this is our time axis. This is n. This is n equal to 0, n equal to 1, 2, 3, 4. Now this is n equal to -1, -2, -3. Let's mark the points. Now this sequence is non-zero only at n equal to 1, n equal to -1. Rest of the samples are 0. So these samples are 0. And delta n plus 1 means simply give a shift towards left to delta n by one sample point. So when we multiply delta n plus 1 with x of n, what's the result? Let's calculate that. So let's compute this result. X of n, delta n plus 1. This is delta n plus 1. So let's mark the points first. N equal to 0 point, n equal to 1, n equal to 2, n equal to 3, and so on. This is n equal to -1, -2, and so on. Now when we multiply x of n with delta n plus 1, what we'll get? We'll get starting with n equal to 0 point. You can check delta n plus 1 is 0. This is 1, so 0 multiplied by 1 is 0. We use a different marker. So this is 0. Similarly, when n is 1, this is 0. But you can check the value is -3 by 2. So 0 multiplied by -3 by 2 is 0. The rest of the samples are again 0. So this is 0. And similarly, when we go for negative values, means when n is equal to -1, the value of delta n plus 1 is 1. And the value of x of n is 2. So this will be 1 multiplied by 2. 1 multiplied by 2 is 2. So that's this. Now when n is equal to -2, the value of delta n plus 1 is 0. The value of x of n is 0. So you can say these samples are 0. And the rest of the samples will again be 0. So what do we have from this? So when we multiply x of n with delta n plus 1, what it did, it simply sampled the value of x of n at n equal to -1. You can check that. This is the value of the sequence when n is, this is the value of x of n when n is equal to -1. So it sampled the value. So what's this doing? What if you have a look at these three multiplications? When you multiplied x of n with delta n, what it did, it sampled the value of x of n when n is equal to 0. You can check it. Gave you the value when n is equal to 0, means of x of n. You can check it, gave you that value. Similarly, when you multiplied x of n with delta n minus 1, it sampled the value of sequence x of n when n is equal to 1. You can check it, gave you that value. Similarly, when n is equal to -1, means when you multiplied the sequence this x of n with delta n plus 1, it sampled the value of the sequence x of n when n is equal to -1. You can check if the value is the same as that of x of -1. So what's this function doing when you do the multiplication of delta sequence and it is shifted versions? It is simply sampling the values. It's simply sampling the values. Now, what do I have? I have x of n. I have x of n. Let me write it. You can use the graphical illustration or you can use simply the functional form. So x of n is simply 2, 1 and -3 by 2. So this is our sequence. So this is my x of n. Now, when you multiply x of n with delta n, it gave you simply 1. The rest of the samples are 0. It sampled that sequence. Similarly, when you multiplied x of n with delta n minus 1, it sampled the value of the sequence x of n when n is equal to 1. So it sampled that value. Similarly, when you multiplied x of n with delta n plus 1, it sampled the value of the sequence x of n when n is -1. So this will be 0, this is 2, 0, 0, and 0. So this is our sequence. So now have a look at x of n and these sequences, these multiplied sequences. Have a look at this. You can see x of n is simply equal to the sum of these sequences. If you add these sequences, So if you add these three, x of n delta n, x of n plus into delta n minus 1, and x of n delta n plus 1, you can say x of n is simply equal to the sum of these three multiplications. So you can, from this, you can have a look at this, again and again. This means simply x of n, you can say is equal to x of n delta n plus x of n delta n minus 1, x of n into delta n plus 1. So you obtained x of n by multiplying these sequences. And if you see from this, x of n delta n is same as x of 0 delta n plus x of 1 delta n minus 1 plus x of minus 1 delta n plus 1. Right. So this is, we express this. Now, why I am writing this statement from this statement from this, and this statement from this sequence? Well, how I am doing that? You can see once you multiply the sequence, it only gives you that sample of n to which it is multiplied with that delta. Means where delta is non-zero, it picks only that sample, or it samples that value. That's why delta function is also called as sample function. That's why the name unit sample function or unit sample sequence. That's why it's called a unit sample, means it samples the value of the signal. When you multiply any sequence with delta function, it samples that value. And you can see when you multiplied x of n with delta n, it gives you the value of x of n at n equal to 0. So now, hey, this is the value of x of 0. So x of 0 is not a signal. X of 0 is a value in the sequence. So you can say once you multiply this, x of n does not remain a sequence. It is simply a constant value or merely a sample value of the signal, and you can say it acts as a mere constant from now on. Once you multiplied it with delta n, it becomes a mere constant value. Same is true for this multiplication. So once you multiply x of n with any delta sequence, be it delta n or it is shifted versions, the x of n is merely a constant now. X of that's very important. From now onwards, means once you did this multiplication or once you apply this multiplication operation, x of n does not remain a sequence on the right hand side. Remember, it's a constant or merely a constant. It's merely a mere constant now. All right, so this acts as a constant from this one. Now let's generalize this result. Let me write this statement one more time. Let me write this statement x of n one more time, and let me write the first, the last term first. So this is x of minus 1 delta n. Then I will write x of n delta n plus x. Sorry, this is x of 0. This is x of 0. So this is x of 1 delta n minus 1. So this is our multiply. So this, see, x of n has only three non-zero samples. Now if it has a more non-zero samples, you can sample those values by multiplying it with the corresponding shifted delta function, right? So if it has x of n has more values, you can multiply it with that sample value. See, we can express this in terms of values. What's the value of x of minus 1? It is 2. You can say this is 2 delta n plus 1 plus x of 0 is 1. You can say it is simply delta. X of 1 is minus 3 by 2 and delta n minus 1. Or you can write it like twice delta n plus 1 plus delta n minus 3 by 2 delta n minus 1. So this is how you are expressing this. So you have expressed x of n in terms of delta sequences. Now let's use this sequence for time being. Let's use this sequence. Now if we have more samples in more non-zero samples in x of n, we can repeat this operation and do the same. And in general, and if I generalize x of n, if I generalize x of n from minus infinity to plus infinity, means if I have all the values from minus infinity to plus infinity, how do I express it? I can say x of n is simply, let me use more sample points now. First, let me start with the negative values. plus x of minus 1 delta n plus 1 plus x of 0 delta of n plus x of 1 delta minus 1 plus x of 2 delta n minus 2 plus x of 3 delta n minus 3. So this is when you have non-zero sample values from minus 3 to plus 3. Or in general, if you have values from minus infinity to plus infinity, you can do this operation. So you have expressed x of n in terms of delta sequences. Now, if I write this right-hand side in terms of a sum, so I can say this is x of k delta n minus k, where k is running from minus infinity to plus infinity. So I can express this right-hand side, this entire right-hand side by using this simple sum. So this is the sum. So I have expressed x of n as a weighted sum of delta sequences. What is the weight? Weight is the corresponding sample value of the sequence, remember. So I have expressed x of n as a weighted sum of delta sequences, as a weighted sum of delta sequences. That's what we have done here, as a weighted sum of delta sequences are simply unit step sequences, delta sequences. That's what we have done. And what's the weight? What's the applied weight? Applied weight is x of n value, means nth value. That's the weight applied here. Please try to understand this. This x of n, once you multiply x of n with any delta, then so once you multiply x of n with any delta, this is x of 0 delta n, means now delta n is the sequence, x of 0 is merely a constant. So please understand, have a look at this sum. This simply means you have expressed x of n in terms of delta sequences, and this is a weighted sum. And what's the weight? Weight is x of nth value, means nth value that we have written here as k. All right. So I hope this is clear. This is how we express any sequence in terms of delta sequences. Now, here are some assignments for you. So please follow these yourself. Let's suppose the values are 2, 0, 3, minus 2, 1. So this is our sequence. 1, 2, minus 1 by 2, 3 by 2, 5 and 4. And let's suppose this is the origin. And third example, we can say 1, 1 and 2. And please solve it using this first graphical approach. Then you can do it directly. Then you can do it. If you once you are familiarized with this, you can write directly the delta function. See, for example, if we repeat this, what was our sequence? Our given sequence. Let me illustrate that again. So x of n is, what's x of n? 2, 1 and minus 3 by 2, and we can write it like this in terms of sequence. This is x of minus 1 delta n plus 1 plus x of 0 delta n plus x of 1 and delta n minus 1. So you know x of minus 1 is, you can see x of minus 1 is 2, so you can say 2 delta n plus 1. X of 0 is 1, 1 multiplied by delta n is 1, and x of 1 is minus 3 by 2, so you can write it as minus 3 by 2 delta n minus 1. So this is how you express x of n in terms of this, and that's your assignment. You do it this way. First, try to get the answer graphically. Once you learn it graphically, means do the multiplication step by step to sample any value. Suppose if I want to sample any value, if I want to sample this 5, which delta function I should multiply x with so that I get 5. So you will get the clear idea from there. Which, if I want to sample any point from these sequences, which delta I should multiply x with so that I get that sample value. All right, now one more time I will repeat this. Once you multiply the sequence x of n with any delta function, means be it delta n or its shifted versions, x of n now merely acts as a constant and delta n is the sequence. Please try to answer that question. I mean, find the solution, how it's true. Yes, x of n is now merely a constant and delta n is the sequence. Okay, this is very, very important for convolution formula.